In wave optics, we talk about the wave character of light. So let me take you through the history of light, and we'll see how things develop over the years. So the first is called Newton's theory of light. So Newton was a person with good command over mechanics, and his way of thinking was quite aligned towards the mechanics, or you can say his way of thinking was particle-like characteristic, which he imposed for light as well. So Newton's theory of light talks about the particle behavior of light. Okay. So it talks about particle behavior of light. So just because he was very much influenced with the laws of nature, the laws of motion, so he said that the law of reflection can be described as a perfectly elastic collision between the surface, reflecting surface and light. So if you consider light as a particle which is moving towards a surface, so he simply consider this light as a particle coming towards the surface, and just like we have law of we have a law of collision, that if a collision is perfectly elastic, then the angle of incidence will be same as angle of reflection, right? So with his idea of particle, and with the help of this concept of collision, he was able to explain this phenomena of reflection using the particle character accurately and efficiently without any ambiguity. Okay. Anyway, so he called light as a particle, which particle, and the name of the particle he called corpuscles. Okay. So Newton assumed light as corpuscles, and that's why this is called the Newton corpuscular theory. This is also called Newton's okay. So this idea, okay. So with the help of this idea, he was able to explain. But while explaining the refraction, he simply failed. Yeah. He failed to explain the a refraction, and let me tell you how we feel actually. So he said that, see, why light bends when it goes from one medium to another medium. So he said, okay, if you roll a ball on a table, okay. So if you let a ball to roll down the table, what will happen? After leaving the table, it will bend like this. For some time, it will move in a parabolic path, as you know. So what is happening here? Newton said that, okay, see, just like the ball is bending while going from table to the air, similarly, light will also bend when it will leave one medium and go to another medium. So this was his explanation. But there was a flaw. Okay. And the flaw was, we know that as the ball will roll down, the speed will increase, correct? So the particle here will have greater speed than the particle here. So V2 is going to be more than V1, right?
Yes.
And more velocity means you're traveling in a rarer medium, because the rule is a medium in which the light moves relatively fast is called a rarer medium. A medium in which light moves relatively slow is called denser medium. Okay. So this is like a rarer. And what else we know that if this is the case, then in a rarer medium, light should move away from the normal. What is happening here? It is moving towards the normal,
Yes.
which is in contradiction with the observed Snell's law. So law of refraction, law of refraction using The law of reflection using Newton's idea was in contradiction with. So law of reflection using Newton's idea was in contradiction with.
Observed Snell's law.
Yeah, observed Snell's law. Therefore, his theory was rejected.
Okay.
Okay.
Yes, sir.
So once you give your once one of your explanation fails, you have to leave the idea, and therefore your entire theory will be rejected. Anyway, there are some highlights of corpuscles theory, and what are those highlights? So he said that okay, light is like tiny particles which he called corpuscles, and when these corpuscles hits the retina, it gives the sensation of vision, and different size of corpuscles gives you the different color. So these are like some of the points which he mentioned. Okay.
Yes, sir.
So let me just put all the theory. So I'll just make a point here one by one. So Newton assumed light to be made of rigid, massless, and highly elastic particles called corpuscles. Okay. When these particles falls on retina, it gives sense of vision, different size of corpuscles gives different sense of color. So now what he achieved and what he failed. So you can see here. So with this theory, he was able to explain the rectilinear propagation of light. Okay, as well as law of reflection. What was the drawback?
He was not able to explain the law of refraction.
Refraction. So drawback of this theory, while explaining the phenomenon of refraction. He assumed that light ray will bend towards the normal while going from denser to rarer medium, which is exactly opposite of the experimental observation, I can say. Hence, this theory was rejected.
Sir, but the law of refraction is also like derived using the particular nature of
Yeah,
light.
yeah. It is
Right.
actually, see, it is explain. He tried to explain the bending phenomena, but he was explaining the wrong way. Okay. So the why that's why we are mentioning that why his theory was rejected that time. Okay.
Okay.
So particle nature can explain refraction, but not in the correct way.
As
And
in
what we are
like
writing here,
way
yeah.
Newton explained it.
Pardon?
As in like not in the way Newton explained it.
Yeah, yeah, correct, correct. Particle behavior is a different thing, but the way he explained was different.
Okay, sir.
So this theory was rejected. Okay. So once this got rejected, so the second theory that we have to understand in detail, which is the basis of wave optics, is called the Huygens wave theory. Okay. So this theory was proposed by Huygens in the year 1678. Let me give you the history. In 1678, it's very easy to remember. 1 and then 678. Christian Huygens proposed his theory of light according to this theory. Every luminous source emits a wave. Okay. Every luminous source emits wave. This wave propagate in form of a wave front. I'll come to that. What is wave front? This wave propagate in form of wave fronts. When these wavefront is obstructed by a tiny hole, slit, or you can say aperture, then the unblocked part of wavefront act as secondary source of energy and it recreates new wave front. These new wave front are called wavelets. Just like it's I mean, you can see the kids of a pig is piglets. So when you recreate when the wavefront will recreate the newer wavefront, then it's like a parent and uh, child relation. And this new, I mean, you can say new wavefront we called, or secondary wavefront we call wavelets. Okay.
Yes.
Now there is a restriction that a secondary source when creates the wave, then it is mandatory that this wave can only move in the forward direction, but it can't move in the backward direction. So these wavelets, I'll come to that in a while, can only move in forward direction as that of the original wave. But can't move backward. Okay.
Yes.
So we'll try to understand one by one. And okay, first of all, so we know that every atom will have many orbits. And when an electron goes from the high energy orbit to the low energy orbit, it releases a photon.
Yes.
So the way light is emitted is due to the excitation and de-excitation of electrons within the atom, and that is the sole mechanism by which light is produced. So light is produced due to excitation and de-excitation of electrons within the atom itself. So when an electron goes from high energy to low energy orbit, then it releases the energy in form of an electromagnetic wave. Okay. So this is the way light is produced. So what happens, like if we talk about source, so if we talk about source of light, or you can say any source of energy. So we talk about that two types of source we talk about particularly. So let's talk about the types of source of light. Sources of light. So the first is called the point source. So we have probably the collection of atom in a very tiny volume, and such collection of atom in a tiny volume you can call point source. Or anything having very small dimension compared to the distance at which we are talking about. I mean, its behavior is observed. So if you observe any behavior at a distance far away from the dimension of the object, we call point source. That's the idea. Understood? So
Yes, sir.
any source theoretically can be point source if the distance at which you talk about the observed phenomena is much bigger than the dimension of the object itself, then we call point source. So in this point source, we have infinite number of atoms, and these infinite atoms will have infinite transition going on every micro nanosecond, and this infinite transition will emit infinite photons. So a large number of photons is coming out of this physical object. So we talk about generation. So if I make an interval up to, let's say, 10 nanosecond. So in 10 nanosecond interval, whatever photon will be emitted by the source, those photon we call one generation. Understood what I'm saying? One generation. So a source will emit energy as a, excitation and de-excitation process. So every energy is coming due to one set of de-excitation and one set of de-excitation happening at a very close interval, we call one generation of energy, and they will move or propagate together. As they will propagate, so the one which will leave first will be farthest, because once you are released, once these EM waves are released, it will propagate in vacuum at a speed of light, isn't it?
Yes, sir.
So in time t, it will travel ct distance away. And not only that, it will travel in all directions. So these are called spherical wavefront. What do we call?
Spherical.
So one wavefront represents one generation. Understood?
Oh, yes, sir.
And every photon in that wavefront belongs to one era. So they are born together, they have similar nature. So wavefront is basically called this, it is the set of, points, it's a locus of points at which the wave oscillate in same phase. It means every one on one surface will have similar oscillation, or you can say similar phase in terms of SHM. So every wavefront represents theoretically, locus of points at which the wave which was produced oscillates in same phase. And because of that reason, they have very much a predictable relationship. Okay. So what is wavefront, guys? So what is wavefront? What you can define? What is wavefront? It is the
I mean, sir, the locus of the photons or the points? Sir?
points, locus of points. Because
Or
we talk about wavefront, we talk about the space, right?
yes, sir.
It is the locus of points at which, because see, there is something happening like this, something happening like this, but we are only taking the location. It is the locus of points at which wave oscillates in same phase. Okay.
Yes.
So it is the locus of points at which waves oscillate in same phase. Okay. So every wavefront will represent one generation, and one generation will have a predictable relationship of the phase. So if you know the phase of this guy, you know the phase of this guy, and this guy also.
Yes.
You can easily relate the phase of every person on one wavefront. Okay.
Yes.
So a point source will create a spherical wavefront, and similarly, if you have a line source, so line source means if the distance over which you talk about some observed property, if that distance is very small compared to the dimension of this length of the object, we call line source. So if we talk about line source, then the energy it will emit will travel as a cylindrical wave front. Understood?
Yes.
So it will propagate like this. So in time t, it will travel ct distance in vacuum, but in other medium, it will travel vt because v depends on. Just give me some time. Okay. So you can see there are two types of wavefront. We have cylindrical wavefront and we have spherical wavefront. Now what happens, like these source emit energy at regular intervals. So we can say these sources are also capable of emitting energy, or you can say power. Okay, because energy per second is power. So if they are emitting energy per second, it means they will have some power. So we are assuming that these power are constant. So there is a constant power source P. So whatever energy you emit, that energy will travel away from you. And depending on the shape, energy will keep on spreading on a bigger and bigger area, right? You can see the same photons are spreading on a larger area, right?
Yes, sir.
Because the number of photons emitted per second is fixed. You have emitted, let's say, 1 trillion and trillion of photons, but that photon is fixed. So as you move forward, it will spread out in a way. The intensity of photon or the intensity of energy reaching a point will keep on decreasing as we go away, right? So what is intensity? So if you talk about a point source at a distance r, so if I talk about the intensity at this point P, so first of all, the word intensity we define as amount of energy falling per unit area per unit time. So that is the basic definition of intensity. How much energy is received over an area per unit time, over an unit area, you can say. So the amount of energy received over an unit area per unit time we call intensity. And as we can see clearly that this energy which is emitted is getting is spread out as we move forward. The intensity is bound to decrease because area will grow, right?
Yes, sir.
And del E by del T by definition is called power. So we can say this is power upon the spread. So intensity we can simply write as power upon area, and therefore a power of a source we can assume as constant. In this case, the area will be how much? For point source.
That 4 pi aspirant.
Correct. So we can clearly see that intensity for a constant power source is proportional to inverse of R square. So it will decay very rapidly by the formula 1 by R square. So if I plot a graph of I versus R, it will be something like this, right?
Yes, sir.
So point source is really powerful for close distance, but for large distance, point source is really bad. Okay. So as you go away, the sound will diminish very, very, very fast. And the best example is the earbuds or the earphone. Okay. So in the case of earbuds or earphone, you can hear the music really loud if it is almost sticking to the ear inside part, right? The moment you pull it slightly away, intensity goes down, right?
Yes, sir.
Quite significantly.
Yes, sir.
So it is because of the point source. So every earphone, ear device which you use is a point source because it will have the low range of operation. And for a high range, it will diminish very quickly. Also, we come to know that because intensity and amplitude are related to each other by the relation that intensity is proportional to square of amplitude. Therefore, we can say that I is proportional to a square and a square is inversely proportional to r square. So we can correlate amplitude with distance as well. So since A square is 1 by R square, so we can say A is 1 by R, or you can say product of amplitude and the distance is constant. Understood?
Yes, sir.
So A1 R1 equals to A2 R2. So this relation is also applicable in vector form. You can always relate with this. Or A delta R1 equals to. Okay, so this was a question from Erodov actually, to relate the amplitude and radius vector in the chapter of SHM. Okay. Now, similarly, if you talk about the line source, so if I choose the length of the source as L, in this case, the energy will spread out only up to this value. Okay. So in this case, the energy will spread out over the cylindrical surface. So intensity at a distance R will be how much? The power of the source upon the surface area on which the energy is falling.
Yes.
How much?
Sir, is it only 2 pi r? That is the curved surface area.
Yeah, correct. Because the energy will propagate like this, not up and down.
Okay.
And therefore, intensity in this case is now inversely proportional to R instead of R square, which means the decay will be slower. Okay. So it will decay, but not as quickly as the point source. It will take some more time. And that is why for large distance, line source is preferred. So if you talk about the home theater system, sound system, then you see that they have tall speakers. Tall speakers are actually representing the line source. So they have a lot of speaker put in series combination. So they behave as a line source. So a line source is basically collection of a large number of point source. That's it. And in that case, the fall of intensity will not be very quick. And therefore, at a large distance, it can be heard with great intensity. And that is why in auditoriums, they put the line speaker, okay, line source or line speaker. You might have seen.
Yes.
Okay. So if we talk about sun, I'll talk about this. So this you can see here, this is called the cylindrical wavefront. And we have realized that the cylindrical wavefront I is inversely proportional to R, but it is proportional to A square. So amplitude in this case is 1 by R, so we can say. So the amplitude as a distance, we can write as amplitude at a beginning upon root R. And I can also write here. So for a spherical and cylindrical wavefront, you can see amplitude is a variable quantity and it depends on the distance away from the source. So as you move away from the source, the amplitude will vary over the distance if it is spherical or cylindrical wavefront. So now comes the concept of plane wavefront. So what is plane wavefront?
Sir, for a plane source.
So a plane wavefront is basically a wavefront which is neither diverging nor converging, right? So plane wavefront is not something which we produce actually, it's like a condition. So if we have whether point source or line source, if you go really far away from the source, and if you draw the wavefront, so the if there is some observer here, what he will see is a small part of it,
Yes, sir.
and that small part will appear as plane, right?
Yes. Yes, sir.
So when a wavefront is observed from from a very large distance from the source itself, then it behaves as a plane wavefront. Okay. So to understand this better, we can take the example of sun and earth. So sun is here, and where is the earth? Let's say this is the earth, a tiny planet. And what is the distance between sun and earth? So this distance is called 1 astronomical unit. And 1 AU is the distance that the light, okay, it's a distance between sun and earth, which is equivalent of the distance traveled by light in roughly 8 minutes and 48 seconds, right?
Yes.
So we, for the sake of calculation, we take roughly as 500 seconds. So you can write as C into 500 seconds. And C is roughly 3 into 10 power 8 meter per second into 500. It turns into 1.5 10 power 11 meters. So the 1 astronomical unit is 1.5 into 10 by 11 meters. And this is the distance between the sun and the earth. So although earth is having large dimension, what is the diameter of earth if I take the entire diameter of earth into consideration? So D turns into how much? So earth radius is 6400. So diameter will be how much? Kilometer. So you can see that the 10 power 11 and 10 power 7. How big is that?
Sir,
So
10,000 times. Or
yeah, roughly 10 power.
4 times.
So if I if I put 10,000 Earth between Sun and Earth, then we can get the entire distance covered, right? 10,000 Earth. So we can definitely say that one Earth is very small compared to the distance, right?
Yes, sir.
Okay. So what happens if the light, let's say, even in case of sun, we have a constant energy released. So nuclear fusion reaction takes place in sun, and the energy released in the nuclear fusion is actually radiated by the sun as well. Okay. So sun also emits energy in all directions. So we can also assign a power to this natural source called sun. And in the chapter of radiation, you will come to know this power is actually written as sigma area of sun into fourth power of temperature of sun. So we'll come to know that this is a formula for power of sun. So if we know the temperature, you can also add the power. But anyway, let's P is the power of sun. So when the energy will reach the earth, okay. So near the earth, it is going to be almost flat surface, isn't it?
So,
Hmm.
sir, are you speaking something?
No, 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 just so once we have this object, I'm sorry, once you go away from the sun, if you are near the earth, the wave will appear here as a plane wavefront, and considering the distance, even if you move from this end to this end of Earth, so if the amplitude of this wavefront near the Earth is A by root is called D, and the amplitude of the same thing here will be how much? Root D plus D, correct?
Yes, sir.
But a small capital D is very small, so D is actually much bigger than capital D, so we can say this is roughly same.
Yes, sir.
So for a small distance, when you move away from source by a very small marginal value, then in that duration we never consider the change of amplitude. We consider amplitude to be constant. So a plane wavefront is a way to tell the world that we are not going to change the amplitude. A plane wavefront represents constant amplitude source. That's the whole idea. Okay.
Yes, sir.
So plane wavefront means constant amplitude source. And luckily in our syllabus, we have to deal with only constant amplitude source, not a variable amplitude source. Okay.
Okay.
So we talk about the plane wave. Okay. Okay. So if you talk about the intensity near the Earth, so intensity near Earth due to sun will be how much? The power upon 4 pi d square. Correct?
Yes, sir.
Or you can also call this as a RSE or RES, sun Earth distance. So you can write in more meaningful manner. Okay. So intensity means how much energy is coming to you. And also you need to realize that this energy is coming to you as a plane wavefront. So if this is the Earth, this is the Earth radius. So the energy that we consider, or the way we consider, is like this. Okay. And a plane wavefront means energy will come this way, and the same energy will fall on the Earth. If I is the intensity of this incident wave, this is the cross-sectional area through which energy is passing forward, right? And same energy will fall on the Earth, isn't it? So once you know the intensity, what is the power received? This is the power by the sun. So power received by Earth equals to What you can write? So power means if intensity is power upon area, so what is power means? Intensity into area.
Yes, sir.
Now the question is which area we will take.
Sir, as in like
So if the plane wave is coming, so the area which will fall on the earth, the area which will be part of earth interaction will be how much?
sir, pi r e square.
Yeah, so it is pi r e square. So it is pi r e square. So this is the energy that the earth will receive. So you can write as a power of sun upon. So power received by the earth equals to power of sun upon 4 pi. Pi gets cancelled, so you can get P sun. And also later on we will come to know that from the chapter of radiation that power of sun will be written as sigma, which is called Stephen's constant. Area of sun, which is like sigma 4 pi r sun square. And if you substitute the PS also, sorry, power received equals to sigma 4 pi radius of sun whole square, sigma a 3 power 4 by 4 So earth is going to receive this much energy, okay,
Yes, sir.
per second. This is the energy received per second,
Yes, sir.
because this is the power, right?
Yes.
Okay. So, okay, this is the plane wavefront, and now we can talk about the Huygens principle actually. It says that the the direction of light ray is, or it must be perpendicular to the wavefront. So direction of light ray must be perpendicular to wavefront. So if we draw the plane wavefront, generally we can draw plane wavefront by drawing the line. This is the side view actually, not the front view. So if these are representing the plane wavefront, then the ray will be can represent like this, normal to wavefront. So ray must be perpendicular to all wavefront. So if yellow lines represent the wavefront, then this represents the light ray. And this must be mutually perpendicular. Okay. So if I draw something like a wavefront like this, then the ray will be like this. Okay. You know the so if this is the ray, so this is your so the concept of ray and wavefront is very simple. So let's practice some of them. Yeah, I'll give you some scenarios. Say if you have plane mirror. So if we have a plane mirror like this, and if I draw a wavefront is coming this way. So let's name it a. Draw the reflected wavefront. How the reflected wavefront will look like? Option A.
So it will be like reflected about the, no, like if we draw a horizontal line, it will be like the reflection of that.
Yeah.
Yes, sir. The option. So what is the difference between B and C?
Okay. Difference we can. This is the difference. Well, I think none of these is answer. So Let me remove this option and control this indefinitely. So if we give you the wavefront, you can simply draw a line which is normal to this line. So it will hit the mirror like this, correct?
Yes, sir.
And it will follow the law of reflection. And will go like this, correct? You can draw a normal and you can draw the. And because we know the reflected light, we can draw the wavefront the same fashion. Now we need to understand that which one will come first. So who is reaching the mirror first? C will reach the mirror first, right?
Yes.
Or you can CD will come first. So CD will go away. Okay. So C will come first and C will go away. Now the question is how the C and D will look like. The one who will come first will go away first also. So C will come here. And D will come after some time. And when C will come, so it will become something like this. So this ray will go this way. So the C will be somewhere here on this line. Understood? Because C, if I draw a ray from here, you can see C will go like this, will go like this.
Yes.
So you can clearly see that which line is going to be C. This is your C, right?
Yes, sir.
So the one which will come first will go first also. And because A and C are coming together, then C and A will go. So C will go first. Then A will go because of the way it is arriving at the mirror. Okay. Okay. Similarly, if I draw a lens, and if I draw a plane wavefront coming here, if these are wavefront. Can you draw the wavefront after refraction? You can try this, then I'll draw, you can compare. Then,
Sir, yes, sir.
so because again, if you just do the ray of light, it will bend towards the normal light,
Yes.
and the wavefront must be right angle to the. Is this your answer?
Yes, sir.
Very. Similarly, you can do it for the convex and concave also. You can do it for concave. So if a wavefront is coming this way, then after reflection, the wavefront will go like this.
Yes, sir.
And the last, I can do it here only. Maybe. Okay. So for the last case, if it is a prism, and if plane wavefront is coming this way, after reflection, the wavefront will be curved or plane.
Sir, I'm guessing it's curved.
So if you know the property of
Sir, dispersion.
yeah, I mean prism will only deviate the light, but it will not bend. I mean converge or divert. It will simply bend actually. And simple rule is plane surface means plane wavefront, curved surface means curved wavefront. Okay.
Yes, sir.
So every light ray will, whether it's hitting here or hitting here, both will bend by the same height.
So, yes, sir.
And that is why the wavefront remains plane only. It will simply bend like this. That's it.
Oh,
Okay.
yes, sir.
So this is the wavefront that we need to know how to draw this. We need to also understand that if we have a, let's say, change of medium, let's say this is a rare medium, this is denser. If light is coming this way, so after reflection, what will happen?
Sir, it will bend towards the normal, but then the wavefront will be straight.
Yeah, so it will bend like this.
Yes, sir.
So the new wavefront will be something like this.
Yes, sir.
Now, because every wavefront represents one generation, therefore the phase relationship is only followed for one wavefront. We cannot write the phase relationship between two wavefronts. Okay. This is the most important part that we must remember. So what is that?
So, and I understand what you just said.
So for phase of every point on a single wavefront
Must be the same.
must be same. Phase difference between 2 points, phase difference between 2 points belonging to separate wavefront cannot be predicted. So it is like we can only talk about one generation and you can only relate single generation photons together. You cannot relate two separate wavefront because they belong to two different generations. So there is a generation gap. And therefore, if a wavefront belongs to if two wavefronts belongs to two different generations, they never interfere. So that is the thing that we must remember, that interference is only possible for same generation, not for different generation. Understood?
Yes.
Now we can prove the law of reflection and law of refraction using the Huygens principle. I'll show you in a while. But before that, let's see the idea of wavelets. So visualization of wavelets. So imagine if we have a source and after moving from the source far away, let's say, or I can make it also possible like this. So if I bring a convex lens and if I keep this at a distance of f, then the light ray traveling from the source after reflection becomes like this. So in a way, the light ray become parallel. So we can say the the wavefront which was coming this way, now the same wavefront will go this way. Okay. So now we are able to create the plane wavefront easily without going very far distance. So you can move only, or you can do this arrangement to get the plane wavefront easily. Okay.
Yes.
So for plane wavefront, we are not supposed to move very far always. We can do this trick also and get the plane wavefront.
Mm.
Okay. Now, this plane wavefront is moving forward, and then we bring a barricade. So the entire wavefront is going to be blocked except a tiny part. So this tiny hole you can see, right? Now this can be a hole, this can be a rectangular hole, this can be a circular hole. If the hole is rectangular, we call slit of a small size, of course. And if it is circular, then we just call hole actually. So word slit or a hole refers to the dimension actually. A slit is always rectangular in dimension, and hole is circular mostly. Okay. So hole can be of any shape, but a slit is bound to be a rectangular shape. So once you cut the slit, you allow a small part of energy to go forward. So every point on the wavefront represents secondary source. It means they themselves are source of energy. So depending on the size of the slit, you can allow a part of some source actually. So this dot is representing some source. So bigger the gap, more the dot we can draw, and hence we can say more energy sources available. So gap basically represents how much energy we are allowing to go through. That's it, isn't it? And because it's a, let's say if you think this is a slit is like a line source or point source. A slit is like
Point source. Oh,
a hole is point source. No? A slit is line source.
when you said rectangular, it was like a lengthened
Yeah,
rectangle.
yeah. It's a entire, you can say size. So it's like you make a cut on a paper. You take a blade and make a cut, sharp cut. So that's a tiny rectangular gap you create, right?
Yes.
Very small. So a slit represents a line source. Okay. And therefore, it will create the cylindrical wavefront, but no matter on a two-dimensional paper, all will look like this. So a plane wavefront which is coming here will again become diverging.
Yes.
So a slit is like a line source, and it will and now what we do is because you have blocked the wavefront, this is the actual source. This is the wavefront. This is also wavefront. But once you block it, so for the source, when you block a wavefront, and if you if the wavefront is blocked, then the new source will recreate the wave as per their shape and all. Then this we call wavelets for the source. This is wavelets for the actual source. Understood? So you can call this as S dash. And then moving further, moving further, you may try to block the path and because you allow the, and these you can see there are two now there are two slits actually, there are double slit. This is called double slit. And these two slits are very, very close. How close? It is fraction of millimeter. Understood? How close?
Fraction of a millimeter. Yes.
So essentially, you won't be able to see that these are two distinct. You will see that's one, but it's a fraction of millimeter away. And there is a gap here. This is called the so this is called slit width. And D is called slit separation. And slit separation is much bigger than slit width. So if the D itself is in fraction of millimeters, you can imagine how small is the width part. So the width will be even small, right?
Yes.
And because these are very close, so we can assume that the same wavefront will hit both the gap, right?
Yes.
Because they're very close, so we can assume that a plane part of the wavefront will hit it, isn't it?
Yes.
Because I see in actual diagram it is here and here. So same wavefront will come here, correct?
Sir.
It's in reality these slits are very close, like here and here. Fraction of millimeter. So I cannot draw actually. You can imagine what is the fraction of millimeter and how to make a dot, two dots, which is fraction of millimeter away, and still be some gap. So that's very difficult to imagine.
Yes.
So these are the simplified version. So now this new wavelets will become wavefront for this two new slit, and what will come out of it will become the wavelets for this. So because of this two slit division, both recreate the wave, and that's why the wave will interfere. Can you see the interference? They are like overlapping with each other.
Yes.
So YDAC or any experiment which you perform diffraction, what it does is it actually breaks the wavefront into two or more parts, and this division process is called wavefront division method. So what we have seen here is called wavefront division. We are doing the wavefront division using double slit actually. So there is a very famous experiment called YDSC. So YDSC means a double slit experiment given by the Youngs. It's called it is the given by the Youngs, so it's called the Youngs double slit experiment. And YDSC basically represents the way to divide the wavefront so that they can interfere. And now the question is why we need to divide the wavefront. The answer is simple. If you don't do it, what will happen? Interference will never occur because only one generation can interfere. So what we do is you divide a generation into, you can say male and female, and then they can get married. Okay, but they must belong to same generation. because
Yes.
they have the understanding with each other, so they can interfere. The first wavefront cannot interfere with the second wavefront. So every wavefront will interfere with itself. And that is why you need to divide. So this is called the wavefront division method. And the reason is every wave in a single wavefront will oscillate in the same phase. So they are said to be coherent. Okay. So there is the idea of coherency and coherence. So we'll talk about it also.
Can you just come back in a minute?
Yeah.
No.
Yeah, tell me.
Yes.
Okay, so now what we'll do is we'll see the Huygens principle application to prove the law of reflection and law of refraction. So proof of law of reflection using Huygens principle. So first of all, draw a mirror. And imagine a wavefront is coming, a plane wavefront. So if you take the width of the wavefront as something, let's say W, this is the width actually. And if this wavefront is coming, which end will reach first? The end A, right?
Yes.
And if you think this is like a plain cardboard, so the end A means it will touch a line, right? There is a line going into the plane.
Yes.
So basically, the part which will get obstructed first is the line source, right? And the energy cannot go on the other side because it's a mirror.
Yes.
So this energy will hit the mirror at this point because we know the ray will come at right angle. But once you hit it, you are like a blocked. So this part is blocked. Okay. But once you block it, what will happen? It will start spreading its wavefront in all directions, but not in all, only in 4 directions. So I'll do first all like this. I'll remove the backward one. And this will happen in all directions. Okay. Now, the point A will start spreading its wavefront every direction, and the B will reach after some time, right?
Yes.
So let's say B will reach the mirror in time t, so this will travel with CT, or you can say VT, whatever you can assume the medium. And if it is coming in VT, in the same time, the first wave will, because what is happening is, let me show you something. The instant this will hit, if A has come here A dash, B has come here B dash. So A has hit the mirror, will start spreading out, and B is about to hit the mirror. It will still go forward to hit the mirror. So now if I call this distance as VT, let's say it is hitting after time t. So when B dash will come here as B double dash, at that instant where the A will be, or sorry, where the A dash will be. So A dash will spread out and it will spread in what radius? VT radius. Exactly same. A dash will spread out up to VT radius.
Yes, sir.
And the rule says that the wavefront must be perpendicular. So the B point, and if I join the new point of A dash, it must be perpendicular. The ray must be perpendicular. So, okay, I can change the color. Or you can draw like this. So if this is the incident ray, if we take this as the incident ray, how the reflector will go? Same angle?
Yes, sir.
So basically A dash has reached this point A double dash. And this point called B double dash and A double dash is now oriented like this. And why we are doing this? Because the wave front and the ray must be perpendicular. So the only possible way of drawing is tangent, right? You must draw the tangent to the wave front, because we know tangent and radius are mutually perpendicular, isn't it?
Yes, sir.
So what you can realize that this is also VT. This is 90 degree. This distance I can call S. And if I choose this this angle as I, so this angle is called R. And luckily this I will be same as this I, and this I will be same as this I. You can use the geometry to get the answer. Okay.
Yes, sir.
And then you can add the property of similar triangle. So you can say sine I equals to how much? VT upon S. And if you look at the sine R, it is how much? VT upon S. And because both are same, so you can say sine I, therefore sine I equals to from 1 and 2. Sine I equals to sine R. Okay. Therefore I equals to R. This is the law of reflection. So what we are supposed to do is we have to supposed to draw the wavefront, a new wavefront which is again perpendicular to the ray. And how we figure it out? So we look at the instant when B will hit the mirror and we check how far the reflected wavefront has gone. Okay. And then we draw the tangent, we get the answer. So this is your proof of this reflection using Huygens principle. Similarly, we can prove.
Don't understand like the part where you drew the tangent A dash dash B double dash.
Okay, so see, first of all, the wavefront AB has come to A dash B dash position.
Yes, sir.
At that position, A dash cannot move further.
Yes, sir.
So A dash will act as a source.
Sir, A dash will act as
source, new source, the secondary source.
Okay, sir.
So A dash will reflect and will start moving back to the
Yes.
medium as a new wavefront.
Yes, sir.
And we know because it's a line source, it will create the cylindrical wavefront
Yes, sir.
and it will keep on moving away.
Yes, sir.
But the other end of the wavefront is still moving towards the mirror.
Yes, sir.
So if it is, let's say, if the B dash is touching the mirror at B double dash after time t, then how much it will travel? Vt.
Yes, sir.
In the same time, how much the A dash will travel back into medium?
Again, VT, sir.
And now this, because that is the position of A dash, where A double dash, when B is touching the mirror. So if I join the A double dash and B double dash, then the ray must be perpendicular, no, to the wavefront. The light ray must be perpendicular to wavefront, right?
Yes, sir.
And because we know the light ray is coming this way and it must go this way.
Yes, sir.
So for any circle, the radius and the tangent only can be perpendicular.
Yes, sir.
Understood?
Yes, sir. Understood, sir.
Very good. So next. Hmm. Next part. Proof of law of refraction using Huygens principle. In this case, we have a medium. So let's say this is rarer, this is dense. Okay. So we'll see that rarer means the light can travel faster than denser. So V2 is less than V1. Understood.
Yes.
Now we can take the same scenario. So if a wavefront is coming towards the interface, this is the interface, the red one. So what will happen? If I name it, let's call A again. So this A will reach first, right?
Yes, sir.
The interface.
Yes, sir.
Even when A and B, so if A is arriving at the interface, Now I will name it A dash and B dash. So this angle, if I call I, this will be also I using
Yes.
geometry. No, I need to make a bigger angle. Then it will be possible. Anyway. And now A dash is blocked. It's like intercepted by the interface. So it will become a secondary source. So A dash itself will start creating the wave, but in which direction? Below the A dash, isn't it?
Yes.
Now B dash will reach the interface after some time. We'll say it reaching the interface after time t. So B dash to B double dash is equals to how much distance? B1, because that is the speed and that is the time taken, so it must be the distance. But in the second medium, it will move slower. So the distance traveled in the second medium in the same time will be less. So A dash will spread out up to a, you can say, radius less than V1T, yes or no?
Yes, sir.
What I will do is I'll just remove one part and then just make it a better time. Let me remove all this. Okay. Now, so because it will travel less distance in the same time, so the radius of the wavefront will be V2T, and wherever is A double dash will be on this wavefront only. So
Yes.
the B dash, and if I draw a tangent here, so if you draw a tangent something like this, something like this, can you see the tangent?
Yes, sir.
Because the wave has traveled less than this, so this is, it's very difficult to do. I have taken very small. Okay.
Yes.
So if I call this as R, this will be also R. So you can clearly see that the new wavefront is going to be bigger than the old wavefront, right? This is bigger one. And you can also see the light ray has bent towards the normal, isn't it? How to write this? So this thing is this is V2T. So you can clearly write something here. Sine I will be how much? V1T by S, correct? But if you write sine R, it is V2T by S. And
Yes.
therefore, the sine I by V1 is same as sine R by V2. That's why this is the same. Understood?
Yes.
And the sine I, if you multiply with C, both sides you can see by V1 sine I equals to C by V2 sine R. And C by V is called the refractive index of the medium. So you can call mu1. So this is also called Snell's law. And you can understand the proof of Snell's law by this simple method. Okay. I hope this is clear.
Yes, sir.
So these are the two proofs of Snell's law. Now we'll go to the next theory of light. This is the Huygens theory. We are done with the Huygens. So after Huygens, which came? Which theory of light came into picture? So why after Huygens, long time after Huygens, eventually the electromagnetic idea came into picture, and Maxwell proposed the electromagnetic theory of light. So we call Maxwell theory of light. So basically, Maxwell was working on the electromagnetism. He was not working with light, right? So Maxwell said, okay, if you combine the rules of electricity and magnetism, then there is an interconnection between the two. And using the fundamental equation of electromagnetism, he was able to establish a fundamental constant. So first of all, let me show you what are the fundamental equation. Okay, I forgot to mention that. Okay, why Huygens tensor failed. Okay. In the time of Huygens, when he proposed the wave theory of light, the problem was a wave requires medium was the prevalent idea, because that time the idea of electromagnetism or atom was not there. It was the Newton's era, and we had no idea about the atoms, except the Dalton theory of atom. So the idea of electrodynamic, or you can say electromagnetism, was not existing at that time. So when Huygens said light as a wave, that time people were knowing about the sound wave, and they were also sure that sound requires medium to propagate. So they thought, okay, light should also have the similar property. So light also requires some medium to propagate, because without medium, a wave cannot propagate. That was their idea, which was of course wrong. So because of the lack of development of science by that time, Huygens needs to prove that which medium is prevailing, because people were aware that, okay, a vast portion of space between Earth and Sun is completely empty without any medium. So if light is a wave, then how it is propagating without any medium? So out of this, you can say peer pressure, Huygens proposed a hypothetical medium which he named luminiferous ether. So he said that the entire universe is pervaded with a medium with a extremely high elasticity, and that medium is called luminiferous ether. But he never gave the account for the, mathematical establishment of the same. In fact, he never proved it mathematically or experimentally, and therefore his wave theory was rejected. The pros of the wave theory was that he was able to explain various phenomena of light, like or you can prove like all the wave properties of light, like interference, diffraction, polarization. So interference, diffraction, polarization, reflection, and refraction all can be proved by the Huygens theory. But the thing that Huygens theory cannot prove is the photoelectric effect, Compton effect. Okay. So what light can, what Huygens theory can prove? Everything except the photoelectric effect and Compton effect.
Sir, can't prove.
Pardon?
Sir, can prove or can't prove, sir?
It can't prove. CNT. It cannot. It cannot prove those phenomena actually of light.
Yes.
So let me add on failure of Okay, so just for the some historical knowledge, you should know all this things. The next is okay. Now we can go to the next. Maxwell theory of light. What was Maxwell theory? Maxwell said that light is an electromagnetic wave. Maxwell never said it's a mechanical wave. What he said, it is an, so according to okay. So according to this theory, so light doesn't need because it's an electromagnetic wave, and we know that electromagnetic wave doesn't need any medium for its propagation. So the hygiene principle, which was rejected on the basis of medium, was again got the acceptance after this discovery. Okay.
Yes.
So the flaw of Huygens theory was removed by the Maxwell theory of light. But when Maxwell assumed the light, he was talking about the continuous light. He was not talking about the discreteness. So he assumed the light as some continuous flow of energy in form of electromagnetic wave. So he proposed some equation called Maxwell equation, if you need to know. So Maxwell equation is basically the collection of all the existing law of electromagnetism. So what are the laws of electromagnetism that we know? So the first is the Gauss law. The Gauss law of electrostatics. So according to the Gauss law of electrostatics, we can write E dot dA equals to Q enclosed by epsilon naught, or we can say in differential form del dot, the divergence of E is charge density upon. So this is called integral form of Ohm's law. This is called the differential form of Gauss. Okay. Then what do we have next? So we have second. Gauss law of magnetism, which says that the closed surface B dot dA is always 0, or divergence of B is always why 0? Because we know that monopoles do not exist. So we always have north pole with south pole. So we cannot have isolated north pole. We cannot have isolated south pole. Unlike the charge, in which case we can have only positive charge or only negative charge. In case of magnetism, this is not possible. That is why every lines of force which will emanate from north will come back to south and vice versa. And that is why if you have any magnetic which is enclosed, whatever lines of force will leave the surface will come back, and therefore there is no net flux. So that's why it is 0. And this is called the Gauss law of magnetism. The third is your Ampere's law. We call Ampere circuital law, but we have to modify this. This is called actually called Maxwell. Later on, it is called Maxwell's. Maxwell, not Maxwell. Maxwell Ampere's or Ampere circuital law. So now we say Maxwell because Maxwell never said it. So as per the Ampere law, we know that the line integral of magnetic field over the loop is always equals to how much? It is mu naught into I enclosed. But now we have to increase this definition, extend this definition. We call this as IC plus ID. IC is called the conduction current. An ID I have discussed somewhere in current chapter called displacement current.
Yes.
So in empty space, we don't have charge, we have only wave. So EM wave creates the displacement current. So in empty space, this will reduce to, so we can write as B dot so when we solve the question, then we take IC equals to 0 and we solve for only IT. And the last is the fourth one is called Faraday's law. Here also we have the differential form. So this becomes del cross B equals to mu naught into, it becomes current density plus, and how to add this one? The rate of change of electric field. Like this, something like this. So this is the differential form. Let me verify this just in case if I'm wrong. Yeah, that's correct. And the last is the Faraday's law, which says that EMF induces how much? So E induces minus del phi E by dt. And how to write this E induce basically? So this you can also write as integration of E dot dl minus d phi by dt. This is the other way of writing. Or in differential form, how to write this? You can write as del cross E. So a line in this is called line integral. Line integral. So surface integral becomes divergence and line integral becomes convergence. Sorry, you can say a curl actually, not convergence, it's called curl. So del cross E will be equals to minus, and because this is the sorry magnetic flux, so we cannot have this del V by del. Okay, so this is very simple formula. So del cross E is minus del V by del T. This is the differential form of Faraday's law. Okay,
Yes.
these are four equations of Faraday. I mean Maxwell equation, and you just need to know all these equations. So when you solve this equation, which I will solve for sure in the chapter of EM wave, not now. So solving all four equations, Maxwell derived a constant C equivalent of 1 by, and when he substituted the value of mu naught and epsilon naught, this roughly came out to be how much? Now Maxwell never said this as light, but fortunately this value of C, when he got from the solving this four equation and the speed of light, which was experimentally determined by Foucault and other physio, both comes out to be same value. And this striking similarity of the value forced Maxwell to think that light must be an electromagnetic wave, because the same answer he is getting from the electromagnetism, isn't it? The laws of electrostatics and magnetism is giving you the answer. So it means it must be electromagnetic. That's why this is happening. So this was some accidental discovery. Okay, Maxwell was not able to realize that okay, he is going to talk about light. He was just doing the electromagnetism, and then fortunately one fine day when he got C, that C, because it was matching with the experimental value of light also. So from that time onwards, this constant, and you can say this is called Maxwellian constant or fundamental constant of nature. This constant was now the new acronym, or you cannot new symbol for speed of light. So it became symbol for light after this discovery. Understood? So it was not C was not speed of light. C was some just a constant which he got in this derivation, and the striking similarity forced him to think that light is an electromagnetic wave, and because electromagnetic wave doesn't need a medium, therefore the requirement of medium is gone. Okay,
Okay.
I hope this is clear.
Yes.
In fact, the idea of a refractive index lies in the electromagnetic interaction of light with matter. So light is electromagnetic. Every matter will have some electromagnetic property, and the interaction of these two, you can say medium, the light, the field of light, and the electric or magnetic properties of medium is giving rise to the idea of a refractive index. And in fact, the refractive index of a medium we write as C by V, and the V of a medium we write as 1 by mu epsilon. Okay, so that's confusing. Let's call the refractive index as so this mu will confuse you with the mu of the uh, magnetism. So so the refractive index is the ratio of speed of light in a vacuum upon speed of light in a medium. And because vacuum, the light moves faster, so this ratio is always more than 1. The way of writing is this. And we know that mu by mu naught is called mu relative. And this relative, this is the definition of a refractive index. Okay, just you need to know this. So next is called the Planck's theory. Now comes the quantum world. So Bohr has, defined the atom, and now Planck is saying, okay, if this is atom, then I'm ready. So Planck's theory of light. Unlike Maxwell, Planck never assumed the light to be continuous. He assumed this as a bundles of energy, some localized bundles of energy. So what he defined, let me try to see. Yeah.
Sir, in previous page, he introduced its D5, D, right?
Yeah. Every time I'm making this mistake. For your correction. D5 B by dt. So what Planck said that according to this theory, light consists of localized energy bundles called photons. Okay. And energy of photon is directly proportional to the frequency. So we cannot E equals to H nu here is frequency constant HF, the way you want. So this is a very famous H is called Planck's constant. And the value of H is how much? 6.626 10 raised to power minus 34 joules. Okay.
Yes.
Now the benefit of this theory was Planck was able to explain the photoelectric effect and Compton's effect, but he failed to explain the other effect. Like the thing which rest of the theory was missing, he was able to explain, but he failed to explain the rest of the things. Okay. So he failed to explain interference, diffraction, polarization, Okay, but he was able to explain reflection and reflection both, even using the this thing. So you can mention this using this theory. So now you remember that the particle behavior of uh, Newton and particle of Planck is different, right?
Yes, sir.
So using this theory, we can explain phenomena like photoelectric effect, Compton's effect, etc. Not etc. Reflection, refraction, but it failed to prove, or you can say explain, failed to explain phenomena like interference, diffraction, polarization. Okay. So now the world was in two teams actually. One, the proponent of wave theory, other the proponent of particle theory of light. And this tug of war continued for quite a long time till the guy called Sir Albert Einstein came and he gave the modern theory of light, according to which the light can behave or exhibit dual character. It can sometimes behave as wave as well as it can behave as particle. So both the you can say characteristic is possible for light to exhibit. So light is really mysterious. It can behave in both ways. And that was the end of the theory of light. So I could just put a modern theory. I don't have a space left to write also. Okay. So with this, he ended the war between the two teams, and he said, "Okay, let's rejoice both the theory together. When it is required to be called wave, call it wave, and if particle, then call it particle. Don't fight. Okay, life is short. Let's be happy." So this was the history of light. I hope you have seen how things got developed over the time. And the next lecture will start the actual wave optics. Okay.
Yes.
See you in the next lecture. Bye and take care.
Yes, sir. Bye, sir. Thank you, sir.